After that fantastic introduction, it is my pleasure to show you guys Discovery Live live. And the reason, and note carefully, that I said show, technology like this, and we're very excited about it, is something that has to be seen and experienced to be believed. So that's why today, on this laptop sitting in front of you, we are going to run 50 simulations in the next 15 minutes. So stay tuned. One thing to note before we dive right in, please pay careful attention. What I'm about to show you moves very quickly. Simulation is not usually this fast, so if you don't watch, you might miss it. So, to begin, let's start with a CAD model. This is a model of a number of vents inside of a radiator, the kind of thing you would find inside of an automotive dashboard. So what if I could show you where running simulation was as easy as applying a boundary condition. So we're going to apply a boundary condition. Let's say we apply here a velocity. We type in a number. Then, just so that you can see the results, we'll move to the front here, and we'll turn them on and change to a composite display. The only thing I have to do is hit a big button at the bottom. This button that's labeled play. What you're now seeing right in front of your eyes, live, is a full 3D simulation. This is not pre-computed. There was no meshing. You watched me type in a boundary condition and a solution appear. So that's pretty good, but we can do better. What if, second, all of the display of results, while this is solving in real time, were interactive? What if I could view any type of post-processing from streamlines to particles, and I could do all of this while the simulation runs and interactively? Now we can do even more. What if, we'll turn back on this display of results. What if I could look at the geometry itself inside of this simulation while it runs? And what if I could start to change it? So let's take maybe these vents that appear here in the middle of this flow. And I'll select them. And watch. This is what I said, pay attention. You don't want to miss it. Let's go ahead and actually rotate these. And the moment that I let go, the simulation updates. So this proves to you in a single tool with instantaneous results, interactivity of display and post-processing. And by the way, we'll never use the word post-processing again because it's no longer post, it's now during. And then full direct connection to geometry. So that's just a preview. Let's start from the beginning. So here's another model. This is an entire assembly, right? With a lot of detail in it. In fact, this is an assembly that includes a model of a GPU. So I love graphics cards, as you'll quickly learn by the end of this presentation just why. But here we have a full model of this thing. Let's study this from a number of different aspects. Imagine that you're a designer. Maybe you care about the thermal dissipation of this GPU, maybe the fluid flow through the enclosure, maybe it's vibration. This is the kind of GPU that goes inside of autonomous cars, has to travel down the road. So to start, let's grab everything that's in this setup of this board, including the heatsink, and let's run a modal solution on it. All I have to do is pick from one of 4 included types of physics, specify a material. I can, of course, assign multiple materials for different elements inside here if I really like. And that's it. All I have to do is hit play. What you're now viewing live is a modal result. You can even see it converging in real time to your right. So you'll see that that first mode frequency is going down. Maybe to make it a little bit clearer, we'll turn off the animation of color. Now you can see it a little bit better. But as usual, there's more. We didn't just solve for one mode. We solved for multiple modes. Here's the second, the third, fourth, right? All the way up to 6. All at the same time. And still, maybe as a designer, I don't just want to view how these are rotating, but actually before that, you might notice. Let's take a look at this first mode. You'll notice here this is free vibration. So let's add more control. Let's pick maybe the support face down here, find all the faces that are the same size. And again, watch this. While this simulation is running, while we're looking at the animation, we can add a boundary condition. Again, pay careful attention. You'll notice suddenly that mode shape is going to change. Now, seeing the modes is useful, but another thing that's useful as a design engineer is being able to look at the location of stresses caused by that mode. So let's quickly, there are tons of displayed results that you can choose from here. Let's pick another one. Let's go look at that stress. And again, we can choose to exaggerate it, right? Here, let's say we do something like this. I have total control. I'm using the interactivity, the live results, and now we'll use the third thing like I keep mentioning to you. Let's go ahead and actually modify the geometry to maybe try to reduce that peak stress. And again, this is really, really cool here, but watch that converge. That is a convergence of an actual solution of a mode problem. Lo and behold, as this continues to iterate, you'll see here that peak stress in that area has now dissipated. Imagine what a designer can do when you can learn something instantaneously, make a change, and evaluate whether that change improved your design. But let's do more. So, another key element of this design here is this big heatsink. So NVIDIA put this whole big metal heatsink, and to me it looks fairly simple. So I wonder if we can do better. Let's delete theirs. Let's create one of our own. So to do this, let's take maybe these faces that appear here and make a copy of them. And oh, by the way, I want my heatsink to be blue. It's my favorite color, so we'll go with that. And then we'll go ahead and we'll start extruding this. So let's say that we take this and we start to create our heatsink. So this will be the base of it. Very simple, no problem. Now the first thing I'm going to do is I'm going to add physics, because when I create ideas and explore them as a designer, physics should be there from step one. So we're going to add another solution within this document, this time a thermal study. We'll say that my heat sink's made out of aluminum. Okay? That's it. That's the only thing I had to pick as a designer. Next, we will go ahead and we'll model a contact region, right? Which part is going to be touching that chip, the part that's going to be hot. Then I'll pick this face, and we'll assign one and only one boundary condition. So let's say we apply the amount of heat in watts that's being generated by that GPU. They do get hot, by the way. Now you'll notice, as soon as I do this, instantaneously, we see a result. In fact, I can start to answer questions. One question I can answer as a designer is, how hot is this heatsink going to get? And right now, I see it gets up to about 132 degrees C. That's pretty hot. And if we look at my heatsink, it's not a very good design. So why don't we improve it? And while we improve it, another tool that you can have inside this software is the ability to chart and measure numerical values so that when you make changes, you can start to compare them. So let's add this chart. And the thing I've chosen to chart is that peak temperature. So now let's model. Let's design. But this is now physics-driven design. So to start, let's go ahead and add maybe a simple fin in the middle of my heatsink. Notice that each time I make a change, the physics updates instantaneously, and I see the resulting performance. I'm down to 105 degrees. We're going in the right direction, but we need to do better. Let's add another fin on this side, maybe one on this side as well. Again, even though I'm designing in the context of an assembly, by the way, right? I have the entire assembly around me. I have instantaneous physics, and I have updated performance. We're down to 78 degrees. But now, and this is what gets me really excited, the power in design is not just in the ability to take a single idea, but in the ability to explore multiple ideas. So let's say, as something different, let's mark the spot that's hot in the middle of this. That's the place where I want my heatsink to be centered. And then let's explore a different idea, whatever it is that pops into my head. In this case, maybe my idea is to create a radial pattern of fins. And to do this, it's not very difficult either. Here I'll select this entire piece, and then I'll use the ability to create radial patterns to pattern around that circle that I just created. You'll see a preview appear, I hit enter, and now I've got a bunch. Even though the geometry gets more complex, and here we could change this to be 15 instead of 8, each time I update this, you see updated performance. So now a completely different idea with completely different geometry still results in a similar performance. I wonder if I could make it better. This, again, for me, is where the power of experimentation comes in, right? As fast as I can push and pull on this. Here I can select maybe these edges and use the included modeling tools to move things around. Again, as fast as I want, as easy as it is, this is the first real-time interactive design environment. But let's go a little bit further. Let's do one other crazy thing on this idea, just because I can. Let's go ahead and put maybe a big piece of metal through the middle of this, just to illustrate, again, how it's possible to take whatever idea that's in your head, give it shape, and evaluate its function. All right, so here's our heatsink. But why don't we take it inside of this entire closure with all these detailed parts and look at its fluid behavior, right? So we did modal, structural, thermal. Let's do fluid in the same context too. So to do that, again, this is pretty simple. All we do is flip over to a fluid simulation. In this case, I will assign a boundary condition. So we'll pick the faces on this heatsink and assign a temperature. Let's say we use the temperature that we just got from the previous thermal simulation. And now we'll also add gravity effects. And we'll change to, excuse me, a composite display. So what you're now viewing, so we got this all right, is the heat moving through the volume and rising in the enclosure. Check that out. From the heatsink that we just made, that we just designed. And maybe we could go even a little bit farther. Maybe, just because I can, let's turn the fans on inside this enclosure. All right? So we'll hide this one. And we'll come over here and select a few set of boundary conditions. We tried to keep boundary conditions really simple because this tool is tailored at designers, right? So we'll specify a velocity, maybe something like 4 meters per second. So suddenly we turned on this flow. And actually, we were looking at velocity the entire time. Let's look at temperature instead. So what you're viewing now is the heat rising up, and soon you'll see the fan pushing this downstream. Oh, let's actually change like that. Just fine. Now, all of the result displays that we used in all the other places, they're consistent. So no matter what you do as a designer, you don't have to learn a different set of tools, a different set of ways of interacting with the results. Right? Here we can actually see the fluid flow. Again, if we wanted to use the included slice plane, we could do that. But let's move on. Let's look at one final example. So this example is big. There are 16,281 faces on this engine block that appear right here. Let's imagine that as a designer, I want to get a feel for how it behaves. So, ignoring, of course, this other one, moving on, let's pick the bottom that appears at the bottom and say, let's add physics, because we're always talking about adding physics. And we'll do a thermal study. We pick a material. Let's say this is a cast iron block, right? Now, where should we apply a boundary condition? I think that probably these cylinders that appear here in the middle are a good place to apply an amount of heat. It's going to be generated. We know combustion's going on there. It's really going to generate a lot of heat. So we'll let this open up. We'll give it 2 more seconds. We do think it will run. If not, we may move on to another one at the same time. Aha! All right. By default, this is thrown into convection. You can change any of these defaults that we pick. But we'll assign, just like I mentioned, one boundary condition to illustrate. And we'll pick all of these cylinders because we can. And we'll assign that heat flow. Let's say, in this case, it's going to be a lot. Maybe 2,000 watts, 2 kilowatts of power that's going to be assigned here. This is the other copy we opened. It took me longer to open the file, longer to type in the number, but the results are still instantaneous. Now, let's go one last final step further. So I put this engine block, right? And we can also do transient analysis. So we can look at not just how the heat ends up, but how it gets there. This is the kind of intuition that we want to be able to build with designers. We want them to understand the behavior part. We want them to be able to graph it. Let's say I want to add a calculator that's maybe the maximum temperature and the volume, right? So if I rerun this transient study, and believe me, it's resolving at each step, you can actually plot and see how long it takes to get to that final temperature. In fact, in this case, it'll take about 5 minutes. These are the types of questions that you might want to know as a designer. Do you care if it takes 5 minutes and 5 seconds versus 5 minutes and 10 seconds? No, not really. What you care about is being able to answer general questions in a very small amount of time. So, as a last single thing, I put this engine block inside of an actual model of an entire truck. Right? The engine's in there. Heaven forbid that we should have to change files here. So let's add another simulation here. Let's do a fluid study around this entire vehicle with all the assembly. Interactively, we can pick a direction that the air comes in, pick a ground plane, and then watch simulation happen. Now, you'll notice we automatically pick a size and a volume for this wind tunnel, but if you don't like it, as a designer, we are under the philosophy that we want to make it possible for you to change things. Everything should be interactive, not just the physics, but also the setup and the definition. So let's make this a little bit shorter. And as a last thing, let's make it wider. So we have a little more space in here. You'll see in just a second why I'm going to do that. But before we do this, I'm going to turn on one of my favorite displays here. This is what we call a composite display. All right, and this is a great way to visualize what's going on with this truck. You can actually see some of the transient effects that go on. It's really quite incredible. All right, so this shows you what's being simulated. You can see the wind moving over the vehicle, creating a bit of turbulence in the back and then downstream. So what if, the last example, physics, and this is what you should keep in mind for every designer, was so easy that during a simulation like this, you could take the entire vehicle and copy it. In this case, I've only moved it, so that's fine. No harm, no foul. We're all about that. But let's actually make a copy this time. Imagine that we put 2 trucks next to each other. With Discovery Live, physics simulation from ANSYS is getting a lot easier. And we think when simulation becomes this easy, this fast, it'll have a profound effect on the way the design is done. So let's move on and talk a little bit about what you just saw. So from a technology standpoint, you saw something that is extremely fast, fundamentally easier to use, includes embedded geometry, and is interactive in every way that we possibly could make it. Second, it's powered by graphics cards. And again, okay, I'll talk a little bit more about this, but the power of graphics cards these days is of an order of magnitude more computational power than what you find in any local CPU. All the demo, all the simulation we just did was done on this laptop sitting here. No remote HPC, no cloud, it's all running here. But all of this is irrelevant. What matters is the value to a user, to a designer. How much faster can I design? How many more designs can I explore? This is what matters, and this is what we think this unlocks. In fact, some of the most famous designers in the world validate just how important it is to be able to explore many, many ideas. Now, there's another aspect of testing many ideas that I think is very important, and that's the following. We very often plan our changes. When I visit customers and visit organizations and see how they do design, they say, we're going to build this. And then they adjust it along the way, but they still build the thing originally that they planned to build. What I think is potentially more important is the ability to test unpromising ideas. Ideas that at first didn't look like they would work out. Now, you would never test those today because the cost of testing them is too high. But when we lower that bar far enough, I think we unlock a big potential for innovation. So, 2 last things to leave you with. 1, there are a number of customers who've tried this. This software is available today for free during a limited tech preview period. So rush out and get it. But here's an example of how one of those customers used it. They took the entire vehicle here, right? 18-wheeler carrying a bunch of machinery. That's what this company builds. And this guy specifically works on transport. And he didn't want to answer a very specific engineering question. In fact, he probably wouldn't even think of himself as an engineer. He might think of himself as a test person, somebody trying to uncover problems. Maybe he might use the word designer. But what he did is to answer the simple question of which is the best way to carry the equipment as we go down the road. And with Discovery, as you just saw, switching the entire position of things, flipping them around, can be done very, very quickly and can answer these types of questions. So lastly, one of the well-esteemed colleagues, Aldine, who writes a well-known 3D design magazine. We showed him this, he certainly got very excited. You can read it for yourself. But the only quote I'll leave you with is the one at the bottom that he said as well when he published this. Trust me, it'll blow your mind. Thank you.